Today we will be solving the graph of the original and finding the derivative, sketching the derivative of this graph. Finding the derivative from the original function requires a sign table. A sign table is what you would have learned in year 9 or 10 when sketching standard degree polynomials of third degree or higher. But we're going to use this and apply this to the derivative. The derivative, which is this, describes the gradient at an instantaneous point. So, if we were to use the gradient of each graph and analyze it at its respective points, you will get the graph of the derivative. To do this, you have to use a sign table, like I said. So, even though you don't have specific values, let's just make these -2 and 2. You can analyze the inflection points and the stationary points of each of these. However, there is important to note that the inflection point is different for respective functions. What I'm trying to say here is the inflection point of one curve, which changes concavity, can have a non-zero gradient, but this one, which is called a stationary inflection point, has a zero gradient. So just be aware that this is different and will cause the gradient graph to be different. But first of all, write f of x and f prime of x. As you can see, you will need to write this, the neighborhoods of respective functions. So what do I mean by a neighborhood? Neighborhood states that what is the function's values around. So -2, the function is increasing, as you can see. So we could draw it, we could say it is increasing. And if our gradient is increasing, according to the derivative, it will be positive. However, at x equals -2, you can see when you take the gradient at that instantaneous point, it will be 0. So our function will flatline and our gradient will be 0. Then from -2 to 2, you can see that we have an inflection point. This inflection point is just called an inflection point. It means when there's a concave down to a concave up, or a concave up to a concave down. And by doing this, we can see that from -2 to 2, the gradient will be negative. Oh, wait, my bad, but it's supposed to be here. And because f of x is decreasing, our function, the derivative, will be negative. This also means that this is a relative max, because as you can see, this is the maximum value such that it has a turning point, just for note's sake purposes. Then, you can see that 2 is actually also an inflection point because it has that concave up to concave down, but the gradient is weirdly 0. So, this is called a stationary inflection point, like what I said earlier. This is very important in graphing the derivative. You can skip out this derivative, this inflection point, but you cannot skip out the stationary inflection points when you're trying to graph. So, when function x, 2, it will also just flatline. And values after 2, which I'll just say as ... there's no reason. You could put any values, -3, -4, -2.1, it doesn't matter. After you put 2, the function still decreases. This is called a stationary inflection point. And therefore, our gradient will still be negative. And by following this sign table, now we can finally graph the derivative. Also, for note-taking purposes, this is the stationary inflection. So, this represents the concave up and concave down, sorry. This represents the stationary inflection. So now, once we have this f prime of x, from our f of x, we can now sketch. By the way, I got this question from Black Red Pen video, Calculus Basics for... Yeah, I'll just put the link down in the description if you want it. So anyways, we will have our -2 and 2. As you can see, f prime of x will just equal to 0. because it's a stationary point, so it will be our x-intercepts. You can label them if you want, I'm just drawing a rough sketch. Then, you can see that f prime of x is positive. That means it is above the graph. If you did regions in year 9, you can understand this, because anything above is positive, anything below is negative. Therefore, we can just sketch one part, like this. But now, we need to see that at around -1, there's an inflection point, not a stationary inflection point. Be sure to be specific when you're relating to these inflection points. And any inflection point will be a turning point on the graph. This is a fundamental theorem. So, there we go. And this is our stationary point. And now, at x equals 2, you may be wondering that how would it look like if it was a stationary inflection point? When a stationary inflection point occurs, f prime of x will equal to 0. But also, f prime prime of x will also equal to 0. So you may be wondering, what will it look like? But by theory, you can see that if it was an x-intercept, and if it was a stationary point, it's both of them. So it will have kind of like a multiplicity of 2, like this parabola, or like a x to the power 4. It has a turning point at 0, it will just turn back up. And it's technically also an x-intercept, which is why you can use that to your advantage. And now you can clearly see what's going to happen. You see this concave down, you see this concave up, you match the y-intercepts, and boom. That's how you get the graph of the derivative. Well, this was a fairly simple topic to analyze, because you're basically just talking about how the gradient changes over time, and this is a representation of that gradient changing across times. And this is why you see an inflection point as the stationary point in the derivatives, and you see the increasing, decreasing functions all linked to it. Let's look at another example where it's not as simple. For example, if we draw the original function with a asymptote, what will happen? There is a special case for this, and I'll showcase it to you right now. Example, it has a y-intercept at 1. Y asymptote, and it has a stationary point here, and the function looks like this. What do you think will happen to the gradient? So, upon discovery, you will see that there's a stationary point here. You can label this as the x-intercepts, and you can have inflection points here because they change in concavity. These are all just basic inflection points. These are not stationary inflection points. Basically, once you've discovered this, you can also say that as you analyze the gradient at instantaneous points, it gets flatter and flatter every single time. Same across here. Flatter, flatter, flatter. So, you could also connect this to the end behavior of the asymptote. So as limit, as x approaches positive infinite, y will also approach 1 plus. You can see this because it will be just above as we analyze the limits. As limit x approaches positive infinity, y approaches 1 plus. This connects to the derivative. As f prime of x approaches positive infinity, it will approach 0, but it will never touch it. It's kind of like an asymptote in a sense. But you can see that according to our y equals x and y minus x graphs, this is y equals x for reference, and this is y minus x, you can see that this has a minus x, kind of looking, right? As you go steeper and steeper. So it approaches from the negative until it reaches 0, because it's from negative x. But if it was a positive, then it will be a positive, right? Because a positive will just approach from the positive side. It will not occur to anything. After you found this discovery of the function of x, what you can say is f prime of x will be different. A common misconception is that you will keep this y asymptote, but this is not that accurate, because yes, your domain still stays because you still have values of x that are not allowed, so you can't second order differentiate them. But a y asymptote can change dramatically. For example, if you have x over x plus 1 squared, you could derivative that and you'll find out a whole different function using quotient rule. This is why you don't need to include the asymptotes in your derivative graph. And by doing this, therefore, we have an x-intercept at 0, stationary point here, and another stationary point here. And our gradient will approach like this. It's very interesting to see that y-asymptote has changed, as proven from our earlier discussions. And as you can see, you could draw the derivative timetable if you'd like. But as f of x goes towards, right, you can see that the gradient will be increasing, then decreasing. So therefore, f prime of x will be positive all the way here, so it'll stay up, have that stationary point, then it will go down below the axis. And therefore, this is beautiful. You have a graph that looks like this, with a whole different y asymptote. So, this is how to graph the function, the original function, with respect and to its f prime of x, by transforming the sign table we used earlier in the video and analyzing asymptotes if needed.